Okay, so moving on to problem two. Problem two, we have this little circuit here. We've got a battery. It's a real battery outlined by this dashed line. It has an EMF. So we're assuming it has a constant EMF and a constant internal resistance, okay, which I'm going to represent with the EMF symbol, that curly E, and a lowercase r. And what we're going to do is we are going to put it up, basically run the current through a series of external resistors, okay, and we want to find what the internal resistance of the battery is, okay. So the first thing to do before you and I'll go through the parts of the problem when we get there. But the first thing you want to do basically is analyze this and find out what the equation you're dealing with is going to be, or what the relationship you're dealing with is going to be. So I'm going to go by Kirchhoff's voltage law, okay, and I'm going to go clockwise like that, okay. By Kirchhoff's voltage law, I like to start right behind. Basically, I just like to start here, okay. So this is going from the negative side to the positive side of the battery, okay. By convention, the shorter line is on the negative side of the battery, and the bigger line is on the positive side of the battery, okay. So I'm going to say plus EMF. And I say that about the negative side and the positive side of the battery. If you forgot that, it wouldn't matter for this problem, okay? You'd still get the right equation. You'd still be able to go on and do everything and get the problem right. So don't worry about that. We're going to go plus EMF as we go through this way. And then we're coming around here. We go through the resistor, and there's going to be current going this way, okay? So plus EMF minus I times big R, okay? And then we have current down here. And then we get into the internal resistor, so minus I little r, and then we're back to the beginning of our circuit, or of our loop, so that equals 0. Okay, so that's our equation. Now, how are we going to analyze this? We can, remember, this is our independent variable, okay, and we can also measure current. In fact, the only way we're going to be able to find current is to measure it, okay? So current is going to be measured, okay? So here's the thing. When you have to do this analysis where you're supposed to make a graph, okay, and use the graph to find something, what you're looking for is a linear plot, okay? So let's go through and find and talk about linear plots. A linear plot has an equation y equals mx plus b, where m is the slope and b is the y-intercept. Okay, so what you want to do is you want to take this equation here, whatever equation you got, and massage it. Some of you like the word massage. Massage this into a form where it matches y equals mx plus b, where y and x are data, or let me actually say y and x are derived from data, okay, raw or calculated. And your data for this purpose includes independent variables, okay? So in this case, it includes big R. Remember, you were told in the problem that you have a collection of resistors, okay? And so you can use those resistors. You can use as many of those resistors as you want. So those are your different data points, okay? Those are your different values for independent variable. And then you're going to measure the current for any given resistor, okay? So what you want to do is basically take this equation and massage it into a form that matches this. So what you can see here is I times R is all by itself, and that's all independent variable and measured quantity. So you're going to make that Y, okay? So what I'm actually going to do is take IR and move it to, basically I'm going to go IR, okay? IR, and I'm going to put that on the opposite side of the equation from the rest of this stuff. So I'm going to get IR equals, the EMF is an unknown constant all by itself. That matches what B is, right? We can find B by finding the intercept of this plot, okay? Not that we need to, but we could. And then you go minus IR, take the term that's left, like that. Now this equation here that I've just written in red is the same as this blue equation here, okay? And it matches this form y equals mx plus b, where basically, so I'll do this in blue, okay? I'll say I times r is y, and then I itself is going to be x. And then little r, okay, the slope is going to be negative little r, and b is going to be the EMF, okay? And now, this is actually everything you need for analysis. So now you've got to describe the setup, okay? So we're going to go through and do part A and part B. So for part A, the quantities to be measured, okay? And this is where I'm going to type because this will hopefully go faster if I'm typing, okay? So for part A, okay, measure resistance of each external resistor R using a multimeter, okay? And then also measure current through circuit with that resistor. Okay, measure the current through the system with that using a multimeter. Okay, multimeters can measure current. They can measure resistance. You just flip the switch. I wish we had gotten more time in class to do labs with those. But a multimeter can measure voltage. It can measure current. It can measure resistance. Okay, current through circuit, and they want the symbol for that, so that's capital I, okay? And then for part B, we want the procedure used to determine the internal resistance of the battery. So what's going wrong here? For some reason, there we go. Okay, so I'll just type this in here and worry later about placing the right spot. So B, the procedure used to determine the internal resistance of the battery, okay? So I measure I for a variety, come on, what happened there? Variety of values of R, okay? External resistors, okay? And then we want to plot, we'll make a plot. Now to find out what our plot should be, we're going to look here at our equation, okay? And plots always, remember, plots are always of the form, or your plots are always the form y versus x. You describe them as y versus x. So you could say plot IR on the vertical axis versus I on the horizontal axis, okay? Okay. Provide enough details so their student can replicate the experiment, including any steps necessary to reduce experimental uncertainty. I don't offhand have any steps to reduce experimental uncertainty. Measure I for a variety of values of R, then plot IR on the vertical axis versus I on the horizontal axis. Maybe, yeah, let's see. That's probably what I would go with, okay? And then, actually, that's B and C, really, okay? So, because I actually went into what you plot, okay? So let's move that up there, okay? Part D, what information from the graph would be used, okay, and how it would be used to determine the internal resistance of the battery, okay? So again, right here it is, okay? There's the answer, M equals negative R. So why can't I? There we go. Okay, D. So internal resistance of the battery is negative of the slope of the plot. Okay, that's the easiest way to explain it. Okay. Part E, after completing their calculations, students begin to consider the factors that might have produced uncertainties. They realize they did not take into account the resistance of the wires used to connect the circuit. Okay, so what does that do? Briefly describe how this would affect their calculated value of the internal resistance of the battery. Explain your reasoning. So that would take effect very simply just as extra resistance in the circuit. Okay, so it would be, like, maybe here, okay, you have an extra resistor or whatever, okay, for R for the wires, okay. So the thing is that would add a, just let me see if I can, there we go. I can do it with part E. So come on, return E would add, so wire resistance would be added to the internal resistance of the battery, increasing the calculated value internal resistance. Okay, so that would be my answer to the question. Sorry about that. And that's about all you can do in 15 minutes. You could, the thing to remember here is multimeters can measure voltage, they can measure current, and they can measure resistance. So there are other ways to do this. You could measure the voltage across the resistor, for example, okay? And that would be then V. You can measure the voltage across the resistor and the current through the resistor if you wanted. Voltage across the resistor would actually end up being this, okay? It would be I times R. So that'd just be maybe a faster way to do it rather than calculating IR. But, what I wrote would be perfectly fine, I think. Okay. Oops, sorry. And escape.